In the middle of the Sahara Desert, where temperatures exceed 55 degrees Celsius and rain has not fallen in years, German engineers are pulling millions of liters of fresh, drinkable water out of thin air. Not from underground wells, not from distant rivers, from the atmosphere itself, using technology so advanced it sounds like science fiction. The air above the Sahara Desert contains moisture, invisible water vapor that human lungs can feel but human hands cannot touch. German engineers discovered that even in the driest desert on Earth, the atmosphere holds enough water vapor to sustain entire communities. The challenge was building a machine capable of capturing it at industrial scale. The global water crisis is not a future problem, it is happening right now. Over 2 billion people worldwide lack access to safe drinking water. By 2050, the United Nations estimates that nearly 5 billion people will face severe water scarcity. The regions most affected are exactly the places where conventional water sources simply do not exist. The Sahara Desert stretches over 9 million square kilometers across North Africa. It is the largest hot desert on Earth. Rainfall in some regions averages less than 25 millimeters per year. Underground aquifers are being depleted faster than nature can replenish them. Traditional water solutions have reached their absolute limits in these environments. Communities across the Sahara have survived for centuries by tapping ancient underground water reserves. But those reserves are finite. Wells that once produced abundant water are running dry. Villages that thrived for generations are being abandoned as the last drops of accessible groundwater disappear into the sand. People are dying because there is no water left to find. A German engineering company has developed atmospheric water generation technology that extracts water directly from humid air. The technology works even in desert environments where relative humidity drops below 20%. This breakthrough challenges the fundamental assumption that deserts are simply too dry to produce water through any means other than transportation from distant sources. The core technology relies on a principle called adsorption. Specially engineered hygroscopic materials attract and capture water molecules from the surrounding air. These materials act like molecular sponges, absorbing moisture even when humidity levels are extremely low. German chemists spent over a decade developing materials with water capture efficiency far exceeding anything previously possible. The hygroscopic material at the heart of the system is a modified silica gel enhanced with calcium chloride compounds. This engineered desiccant can absorb up to 40% of its own weight in water from air with humidity as low as 15%. When heated, the captured water is released as pure vapor, which is then condensed into liquid drinking water. The German atmospheric water generators are designed as self-contained modular units. Each unit operates independently, requiring only a power source and ambient air. No external water supply needed, no connection to any municipal infrastructure required. A single unit can be deployed anywhere on Earth where air exists, and air exists everywhere, including the deepest Sahara. The process works in a continuous cycle. During the cooler nighttime hours, when relative humidity naturally increases, the hygroscopic panels are exposed to desert air. The hygroscopic material absorbs moisture throughout the night, accumulating water molecules on its enormous microscopic surface area. By dawn, the panels are saturated with captured atmospheric moisture. As the desert sun rises, temperatures climb rapidly. Solar thermal collectors focus sunlight onto the saturated hygroscopic panels, heating them to temperatures between 65 and 90 degrees Celsius. This heat drives the absorbed water out of the desiccant material as hot vapor. The water has been captured from air and now exists as steam ready for condensation. The condensation system uses radiative cooling panels that dissipate heat into the sky even during daytime. These panels are engineered with nanostructured surfaces that emit thermal radiation at specific wavelengths that pass directly through the atmosphere into outer space. The result is cooling without electricity. The desert sky itself becomes the refrigeration system. Each modular unit produces between 500 and 5,000 liters of water per day, depending on size, configuration, and local humidity conditions. In the Sahara, where nighttime humidity typically ranges between 20 and 40%, a standard commercial unit consistently produces approximately 2,000 liters of clean drinking water every 24 hours. The quality of the water is extraordinary. Because the process captures individual water molecules from air, the resulting liquid contains virtually no dissolved minerals, heavy metals, bacteria, or chemical contaminants. Independent laboratory testing by German standards agencies confirmed that the water exceeds World Health Organization drinking water guidelines across every measured parameter. However, pure distilled water actually lacks essential minerals that the human body requires. German engineers addressed this by integrating a remineralization stage into the system. Controlled amounts of calcium, magnesium, and potassium are added to the condensed water, restoring the mineral balance and natural taste that makes water satisfying and healthful to drink. The energy source powering these desert water generators is the most abundant resource the Sahara possesses: sunlight. Each unit is equipped with high-efficiency photovoltaic solar panels that generate all the electricity needed for fans, pumps, sensors, and control systems. Concentrated solar thermal collectors provide the heat needed to release water from the desiccant material. The solar power system includes battery storage that maintains operation during cloudy periods and powers monitoring systems overnight. The batteries use lithium iron phosphate chemistry, chosen specifically for its stability in extreme desert temperatures. The entire energy system is designed to operate maintenance-free for extended periods in environments where technical support may be days away. The mechanical design of each unit reflects decades of German precision engineering. Every component is manufactured from materials selected for extreme heat resistance, sand abrasion durability, and corrosion prevention. Stainless steel frames, anodized aluminum housings, and UV-stabilized polymer components ensure the units survive decades of exposure to the harshest conditions on Earth. Air intake systems use multi-stage filtration to prevent sand and dust from contaminating the hygroscopic panels. Primary cyclone separators using centrifugal force remove large particles. Secondary HEPA-grade filters capture fine dust down to 0.3 microns. The filtration system protects the delicate desiccant material while allowing maximum airflow for efficient moisture capture. The control system managing each unit is a marvel of automation. Microprocessors continuously monitor ambient temperature, humidity, solar radiation, wind speed, and water production rates. Algorithms optimize the adsorption and desorption cycles in real time, adjusting panel exposure angles, fan speeds, and heating intensity to maximize water output under constantly changing desert conditions. Remote monitoring via satellite communication allows German engineering teams to oversee units deployed thousands of kilometers away. Performance data is transmitted hourly to monitoring centers in Germany. Anomalies are detected automatically. Software updates are pushed remotely. A unit operating in the middle of the Sahara can be diagnosed and adjusted by an engineer sitting in Munich. The first large-scale deployment occurred in collaboration with development organizations operating in sub-Saharan Africa. Multiple units were transported to remote communities in Niger and Chad, where groundwater sources had completely failed. The logistics of delivering industrial equipment to locations with no paved roads, no electricity, and no infrastructure presented its own engineering challenges. Units were designed for flat-pack shipping. Each generator breaks down into components that fit inside standard shipping containers. Assembly at the deployment site requires basic tools and can be completed by trained local technicians within 48 hours. The German team created illustrated assembly guides in multiple languages, including French, Arabic, and local dialects. When the first unit was activated in a village in northern Niger, producing clean water from desert air, the community reaction was overwhelming. Villagers who had been walking over 15 kilometers daily to collect contaminated water from distant sources watched in disbelief as pure water flowed from a machine that seemed to create it from nothing. Children who had suffered from chronic waterborne diseases drank clean water for the first time in their lives. Women who spent 6 hours daily collecting water suddenly had that time returned to them. The village elder called it the machine that drinks the wind. For a community on the edge of survival, the technology was not just impressive, it was salvation. The scalability of the technology is being proven through progressively larger deployments. Village-scale systems serve communities of up to 500 people. Town-scale installations combining multiple units in parallel provide water for several thousand residents. Industrial configurations are being designed for agricultural irrigation, producing tens of thousands of liters daily for desert crop production. Agricultural applications represent the most ambitious frontier. German engineers are testing atmospheric water generation systems coupled directly with precision drip irrigation. The concept is revolutionary, growing food in the desert using water that is manufactured on-site from air. No rivers needed, no wells needed, no rainfall needed, just air, sunlight, and German engineering. Pilot agricultural projects in Morocco have demonstrated that atmospheric water generators can sustain small-scale greenhouse operations in desert environments. Tomatoes, cucumbers, and leafy greens have been successfully grown using exclusively atmosphere-derived water. The produce quality matches or exceeds conventionally irrigated crops because the water purity eliminates soil contamination risks. The economic costs have improved dramatically as the technology matures. First-generation units produced water at approximately 15 euros per cubic meter. Current generation systems have reduced that cost to between 2 and 4 euros per cubic meter. For comparison, trucking water into remote Saharan communities typically costs between 8 and 20 euros per cubic meter. German engineers project that next-generation systems incorporating advanced desiccant materials and improved solar thermal efficiency will reduce production costs below 1.5 euros per cubic meter within 5 years. At that price point, atmospheric water generation becomes economically competitive with conventional water infrastructure, even in regions where wells and pipelines are feasible. The technology has attracted significant investment from both European development agencies and private sector water companies. The German federal government has committed substantial funding through its international development programs. Private investors see the commercial potential in providing water to the estimated 2 billion people currently underserved by conventional water infrastructure worldwide. Competing technologies exist, but face significant limitations in desert environments. Fog collection systems require coastal fog conditions that do not exist inland. Solar desalination requires access to saltwater sources. Traditional atmospheric water generators using refrigeration-based condensation fail below 30% humidity. The German adsorption system overcomes all these limitations. The environmental footprint of the technology is remarkably small. No water is extracted from underground sources, no rivers are diverted, no ecosystems are disrupted. The water is literally manufactured from ambient atmospheric moisture that would otherwise remain as invisible vapor. And the energy comes entirely from solar radiation that would otherwise simply heat the sand. Critics question whether atmospheric water extraction at massive scale could affect local humidity patterns. German climate scientists have modeled the impact and concluded that even thousands of units operating simultaneously would extract less than 0.01% of regional atmospheric moisture. The atmosphere continuously replenishes itself through global circulation patterns, making the supply effectively unlimited. The technology is also being adapted for emergency disaster response. Compact mobile units mounted on trucks can be deployed to earthquake zones, flood-affected areas, or refugee camps within hours, providing immediate clean water supply without requiring any existing infrastructure. The German military has evaluated the technology for field deployment in arid theater operations. Quality monitoring is continuous and automated. Each unit tests its own water output using integrated sensors that measure pH, conductivity, turbidity, and microbial indicators. If any parameter deviates from safe drinking water standards, the system automatically diverts the water for retreatment before releasing it for consumption. No contaminated water ever reaches the end user. Maintenance requirements are intentionally minimized for remote deployment reliability. Air filters are replaced every 6 months. Desiccant panels have a rated lifespan of 5 to 7 years before requiring regeneration or replacement. Solar panels carry standard 25-year performance warranties. The overall system is designed to operate with minimal intervention for a decade or more. Training programs developed by the German engineering team prepare local technicians to perform routine maintenance and basic troubleshooting. These programs run for 2 weeks and include both classroom instruction and hands-on practice with actual units. Graduates receive certification and ongoing remote support. The aim is complete local operational independence within the first year of deployment. The intellectual property behind the technology is protected by over 40 international patents covering desiccant chemistry, solar thermal integration, condensation systems, and control algorithms. However, the German company has committed to licensing the technology at reduced rates for humanitarian deployments in least developed countries. Profit and purpose are being balanced deliberately. Research continues at German universities and private laboratories. Next-generation desiccant materials based on metal organic frameworks show water capture efficiency up to 3 times higher than current silica gel systems. If successfully commercialized, these advanced materials could enable water production even in hyper-arid environments where current systems approach their operational limits. Integration with existing renewable energy infrastructure is expanding the technology's reach. In regions where solar farms already exist, atmospheric water generators can tap into surplus electricity during peak production hours. This parasitic power strategy reduces the cost of dedicated solar installations and accelerates deployment in areas with existing renewable energy commitments. The geopolitical implications are significant. Nations currently dependent on transboundary water sources face constant diplomatic tension over shared rivers and aquifers. Atmospheric water generation offers the possibility of water sovereignty. A nation's water supply could come from its own air above its own territory. No upstream neighbor could threaten that supply. German engineering has a historical tradition of solving problems that others consider impossible. From automotive engineering to renewable energy to industrial manufacturing, the German approach combines theoretical rigor with practical precision. Atmospheric water generation in the Sahara represents the latest chapter in that tradition, turning nothing into something, air into water, desert into life. The machines now operating across the Sahara do not look dramatic. They are modest metal structures covered in solar panels, humming quietly in the desert heat. No towering dams, no massive pipelines. Just precise engineering silently extracting water from air, molecule by molecule. And in their quiet efficiency, they may represent the most important water technology breakthrough of this century. For the communities they serve, these machines are not engineering curiosities. They are lifelines. They are the difference between staying and leaving, between health and sickness, between life and death. German technology pulling water from Saharan air. Proof that human ingenuity, when applied with precision and purpose, can find water even where none seems to exist. What do you think about atmospheric water generation technology? Can machines that pull water from air truly solve the global water crisis? Or is it too expensive, too small scale, and too dependent on technology to make a real difference? Share your thoughts in the comments below. Subscribe and turn on notifications so you never miss another incredible engineering story.